Hi, this is Chiranjeevi. Now I am going to discuss about pericyclic reactions. So if you learn this all table, you can do 90% of the pericyclic reactions easily. Okay? Right. So pericyclic reactions are concerted reactions and they occur through the electrocyclic transition state. No bond breaking and making takes place in pericyclic reactions. Heat or light sensitive reactions. Okay, right. So we have Woodward-Hoffmann rules for electrocyclic reactions. So in that open cyclic and closed cyclic reactions. Okay, in that first system and for electronic systems, 4 and pi electronic system. So rotation is con-rotation, that is allowed only in thermal conditions, and photochemically that is forbidden. And 4 and pi electronic system and rotation, if rotation is this, that is H nu, that means photochemically allowed reaction and thermally forbidden reaction. And if you observe 4n plus 2 pi electron system, that is on con-rotation, photochemically allowed and thermally forbidden. And 4n plus 2 pi electronic system, if on disrotation, thermally allowed reaction and photochemically forbidden reaction. Next, if you observe for electroaddition reactions, if the system is 4 and 5 electronic system, the addition type if supra or anthera, then that reaction is photochemically allowed one and thermally forbidden. And if you observe 4 and pi electronic system, that is supra anthera or anthera supra addition, that reaction is allowed on thermally allowed and photochemically forbidden. And if you observe 4n plus 2 pi electronic system, that is on supra addition or anthera addition, that is allowed thermally and photochemically forbidden one. And if you observe 4n plus 2 pi electronic system, that is supra anthera addition or anthera supra addition, that is photochemically allowed and thermally forbidden one. Next, sigmatropic reactions. If you observe sigmatropic reactions of hydrogen shift, then first we should observe hydrogen shift type of shift, that is 1,3 hydrogen shift, that means it equals to 4 and 5 electronic system. So 1,3 hydrogen shift is if on anthera shift, that is thermally allowed. If that is supra shift, that means hydrogen shift is supra, then that is photochemically allowed. And if you observe 1,5 hydrogen shift, that is that equals to 4 and pi electronic system, the on supra hydrogen shift, that is thermally allowed, and on anthera hydrogen shift, that is photochemically allowed. And if you observe 1,7 hydrogen shift, that equals to 8 pi electronic system, on anthera shift of that hydrogen, it is thermally allowed, and on supra shift of the hydrogen in 1,7 hydrogen shift, that is photochemically allowed. Right. And if you observe hexadiene, so it produces dimethyl cyclobutene in pericyclic reaction or concerted mechanism. If this hexadiene has at one end trans and two ends trans or cis, that is thermally allowed reaction and it forms trans product, and on photochemically allowed reaction it produces cis product. And if we observe trans cis hexadiene, then the product cis product is thermally allowed and trans product is photochemically allowed. And if you observe octatriene, so it produces dimethyl hexadiene. If octatriene has trans or cis, that produces cis product on thermally and trans product on photochemically. If you observe trans cis in octatriene, So trans product is observed in thermally and cis product is observed in photochemically. Okay, so if you remember all these tables, then you can do 90% of the pericyclic reactions easily, okay, in any competitive exams. Okay, first we should know what is can, what is dis, what is supra, what is anthra. Okay, so we should learn first these terms, then only you can solve and you can easily remember these tables. Okay, then first we should observe the orbitals which are involved in pericyclic reactions. So this is p orbital, consider, right, and this is nodal plane, and these two are positive and negative, these are lobes, and this center point is considered as node. Okay, so we can, for our convenience, we can write this is darker shape and this is empty lobe. Okay, right. And if you observe molecular orbitals, we have pi, psi 1, psi 2, psi 3, psi 4, like that. Number of nodes equals to n minus 1. So if molecular orbital is psi 1, so 1 minus 1 is equal to 0, and if it's psi 2, then 2 minus 1 is equal to 1. If psi 3, so 3 minus 1 is equal to 2, and if psi n, then n minus 1. So this number of nodes we can observe in molecular orbitals of different given molecules, right? So on energy diagram, if you take energy diagram, and this is the ground state, so in the ground state, so these two lobes are in one same side and the same lobes are in same side. Okay, then so if you observe at its ground state, so we can consider one, so plane of symmetry. Consider this is the plane of symmetry. So plane of symmetry is possible in ground state pi energy system of this p orbitals. Okay, so and this is symmetry allowed, that's why we can consider plane of symmetry is allowed, that's why symmetry S is present at ground state of pi. Next, on first excited state phi star, so this is the representation of the lobes of the orbitals of this molecule. Consider, so on, if you rotate this orbital on C2 180 degrees, so we can get the same orbitals of this molecule. So that's why on C2 we get symmetry. So at phi star or first excited state of the molecule, in there is no plane of symmetry, that's why it is anti-plane of symmetry, but symmetry is present in if we rotate the orbital through the C2, so that's why symmetry present or symmetry allowed through the C2. Okay, so at ground state plane of symmetry is present, that's why symmetry S is possible. And if you observe C2, there is no C2 in this molecule, so in the ground state, that's why it is anti. And if you observe phi star or excited state of the molecule, the plane of symmetry is absent, that's why anti or absent. And if you observe C2, so C2 is present in a phi star, so that's why symmetry allowed. So this is about symmetries of that in an excited state of molecules, right? And if you observe, for example, I am giving one example, that is 1,3-butadiene, example of acyclic polyene. So this is polyene 1,3-butadiene and n is equal to 4. So that means number of orbitals, molecular orbitals are 4, psi 1, psi 2, psi 3, psi 4. Okay, right. And molecular orbital diagram, so this is the representation of molecular orbital diagram. So and nature of the molecular orbital, consider this is bonding molecular orbital of pi 1, and this is bonding molecular orbital of pi 2, and this one is anti-bonding molecular orbital of phi 1 star, and this one is anti-bonding molecular orbital of phi 2 star. Okay, and number of nodes, already I told you number of nodes is equal to n minus 1. Okay, consider this is psi 1, so that means 1 minus 1, that is equal to 0 nodes. So in molecular diagram, the first ground state of psi1, in psi1 there should be no nodes, so that's why these shaded lobes are all in the same side, and these empty lobes are in same side. That's why there is no lobe. So this is a representation of psi1 of molecular diagram of the 1,3-butadiene. And if you observe psi2 means 2 minus 1, that is equal, number of nodes is equal to 1. So it here in the molecular orbital diagram there should be one node. So that's why we are representing two lobes are in backside which are shaded, and two lobes are upward which are shaded. So that's why here is the present of one node. Okay, so that means here shaded lobe is upside and this shaded lobe is on below of the molecule. That's why here is a representation of one node. And if you observe psi3, and that is in antibonding molecular orbital of phi1 star, so it should have number of nodes 2. So consider here is the one node and here is the one node. Okay, and if you observe in psi4, so psi4 number of nodes is 3, so here is a representation of this. We can observe 3 nodes in this representation of molecular orbital diagram of 1,3-butadiene, 3 nodes. Okay, right. Next, observation of symmetry. If you observe plane of symmetry, sigma of symmetry in this is possible, so that's why symmetry is allowed. So if you go through this, if you cut this molecule like this, so we can observe plane of symmetry in this. And if you observe in second bonding molecular orbital, there is no symmetry, plane of symmetry observed in this representation, that's why anti-symmetry. And if you observe psi3, here is the presence of symmetry, and if you can observe plane of symmetry in this. And if you observe anti-bonding molecular orbital of phi2 star, so there is no symmetry observed in the representation of this molecular orbital diagram of 1,3-butadiene. So there is no plane of symmetry, that's why anti-A. Right. And if you observe C2 or principal axis of symmetry, so in the first psi1, so there is no C2, that's why A. And in psi2 here is the presence of C2 of symmetry, then symmetry is possible. And if you rotate these two orbitals into C2, so we can observe here presence of C2 symmetry, so that's why S. And if you observe in psi3, so there is no C2, that's why anti-symmetry. And you can observe psi4 here is a representation of symmetry, C2 symmetry. Okay, next, and electronic ground state of the 1,3-butadiene. So in the ground state, so there is the pairing of electrons takes place. So we have the 4 states. That means psi1, psi2, psi3, psi4. That's why we have the 4 states, and number of n is equal to 4. That's why. Okay. So in ground state we can observe 4 electrons in two states. So those are in bonding molecular orbitals. So HOMO. This is called HOMO. Why? What is HOMO? HOMO has highly occupied molecular orbital. Once again, highly occupied molecular orbital. So here is a highly occupied molecular orbital in the electronic ground state of the 1,3-butadiene, and this is LUMO. So after the HOMO is LUMO. What is LUMO? Lower unoccupied molecular orbital. So in this representation, so this is the unoccupied molecular representation, that's why this is considered as LUMO. And this is highly occupied molecular orbital, so this is HOMO. Okay. And if you observe electronic first excited state, so in this one electron is excited from the HOMO 2, and this one third level. So in the third level, this is now considered as HOMO, because this is the highly occupied molecular orbital in the levels, energy levels of the 1,3-butadiene, and this is considered as LUMO. Okay, so this is lower unoccupied molecular orbital in the electronic first excited state. This is LUMO. Okay, that is LUMO. So Next, so what is Kahn rotation? So this is the representation of Kahn rotation. So these two orbitals, if we rotate the orbitals in same side, so say if we rotate the orbitals in same side, then that is simply called as Kahn rotation. Next, if you observe this rotation, this is if you rotate orbitals in opposite direction, so opposite direction, then this is called as disrotation. Okay, right. So consider thermal conditions. Frontier molecular orbital approach. We have different methods to consider if the reaction is thermally allowed or photochemically allowed under Kahn rotation or disrotation. So I am explaining an easy way by using frontier molecular orbital approach, that is HOMO-LUMO approach. Okay, consider electrocyclizations. So electrocyclic reactions, this butadiene on heating produces cyclic butadiene. Okay, right. And so this is a representation of the cyclic butadiene. Okay, right. Next, on Kahn rotation of this butadiene. Okay, so first already I given the representation of the butadiene. So you should have the remembrance of this molecular orbital diagram. Already I told you. So HOMO. So this is HOMO. So HOMO means here we have this representation on this. Now we are explaining it. Okay. So on Kahn rotation and the rotation of the orbitals in same direction on Kahn rotation. So if you use under thermal condition, so here I am rotating it and we are getting, so this bonding takes place. So means the same sides of the lobes, the same lobes are bonding here. That means sigma bonding is possible. That means thermally this rotation is allowed. That means thermally on Kahn rotation we can get a proper bonding. That means this reaction is possible on thermal condition. So here on 4n system, so this is 4n system on thermal condition. On 4n system, on Kahn rotation we get the allowed rotation and allowed bonding. Okay, right. And if you observe disrotation or disrotatory motion on the same molecule, so this opposite rotation and disrotation on thermally, if you rotate this molecule, so this lobe comes here and the empty lobe comes here. So we get finally we get this one. So these two lobes are not same. That means this is anti-bonding. So anti-bonding is not, it is repulsive. That means there is no chance of formation of anti-bonding. So that's why this is not allowed. Means 4n system under disrotation. Okay, 4n system under disrotation thermally forbidden or thermally not allowed. Okay.